At least we can restart it because we're right.
Let's restart it? Okay. Hi, I'm Scott Whalen, this is Andrew Noseworthy, this is Bradley Higdon, and this is Brandon New, and we are Vortex Energy. Our team is assembled to design a counter-rotating vertical axis wind turbine array. And here's a little presentation. So we're going to go through an introduction on the project, we're going to talk about some initial research, we're going to talk about our concept selection, we're going to go through some modeling and simulation software, we're going to talk about our experimental plan, we'll talk about the project management plan, then we're going to show you guys path forward. Alright, a little intro. So our main objective is to design and test an array of vertical axis wind turbines that can be used to generate power for a small rural community. Both vertical and horizontal wind turbines have been used all over the world to take up a large amount of real estate. Wind turbines come in many forms, built for various conditions such as wind speed, climate, environmental impact, location conditions, and the amount of available real estate. They can be situated on land or in large bodies of water, and we must consider all this criteria when designing our array. Alright, so some goals. We're going to identify the best array configuration for wind farm power density. We're going to ensure wind farm power density is hard and net for a single horizontal turbine. And we're going to create an implementation strategy for a small rural community. Some constraints we have to deal with. We're going to have to select the turbine type. We're going to have to keep it within our budget. We're going to have to ensure that the turbine has self-starting ability. We are limited in project duration. We're going to have to consider the wind tunnel size and the max wind speed within that wind tunnel, and then we're going to have to consider that in scale testing. So here's some types of single turbines. So these are different vertical axis wind turbines. The first one is a Darius, which was designed by George Darius in 1927. Principle of operation, and it is very limited. The second type is Savonius, designed by S.J. Savonius in 1922. Has a low rotational speed and high torque output, and also uses an emitter. Two other types, which are variations, is the H rotor, which came from the Darius turbine. It was designed in the UK during 1970 and 1980. It's a lift-driven device and operates at various wind speeds. The second variation is the helical, which is a variant from either Darius or Savonius. Torque split evenly over entire revolution and prevents destructive pulsation.
Okay, so after we did some research on vertical axis wind turbine, we decided to also do some extensive research on different type of vertical axis wind turbine array that are currently out there or being investigated. Well, first of all, what is a vertical axis wind turbine array? Well, it simply means a group of vertical axis wind turbines that are arranged within a configuration in a wind farm. And the basis for arranging within a configuration is to ensure that the power produced by that arrangement is optimized. So they are arranged in such a way whereby they interact with each other so that the power output is maximized and more efficient. So we went ahead and did some research on vertical axis wind turbine array, but there really isn't much out there right now in terms of studies going on for arrays. But we did find one that was derived by a scientist called Waze in 1973, and he investigated what we call the fish schooling theory or phenomenon. It basically involves the arrangement of fish within a school and how they interact with the vortex shared by the upstream fish within the school. So the upstream fish, as they navigate through the water, they create certain type of vortices, and the fish downstream interact with those vortices created by the upstream fish, and they use that interaction to navigate through the water in as efficient a way as possible and with as little energy as possible. So what are the benefits of vertical axis wind turbine array over what we currently have, which is the horizontal axis wind turbine array or a vertical axis wind turbine? Well, the first benefit is vertical axis wind turbine array has higher power density. So this is basically the amount of power that can be produced per meter squared within the wind farm. Compared to the horizontal axis wind turbine array, this increase in power density is up to sometimes the order of magnitude higher. The second benefit is when you place two counter-rotating vertical axis wind turbines and make them interact with each other, the power coefficient that they produce is higher than if you place one of those vertical axis wind turbines on its own and allow it to rotate in space. And finally, another benefit, the vertical axis wind turbine array wind farm uses smaller footprint as compared to when you have a horizontal axis wind turbine wind farm. And now I'll hand you over to Brandon, and he will take you to the concept generation.
Okay, after background research, 3 design concepts were generated. Concept A is an array of Savonius type bolts. Concept B is an array of heat-shorter bolts. Concept C is an array of helical type bolts. And all the features and drawbacks were summarized and listed in the above table. For concept selection and evaluation, the concept scoring matrix were used. In total, 7 selection criteria were used. They are simplicity of build, power efficiency, reliability, land usage, environmental impact, and solidity. Each design concept has its own positive and negative attributes. As a result, concept B and C were proceeded for the further evaluation. Concept scoring matrix were used to finalize the final design concept, and each selection criteria was rated differently, and each design concept were weighted in the range from 1 to 5. As a result, concept B, heat-shorter, was decided to use for our final design. So 3D is a highly reliable computational fluid dynamic package. We are going to use this computer software to simulate both experimental and real environment. So as the end, we will generate some 3D animation and 2D plot, such as some velocity profile and pressure profile. And then we will use this result to determine the best array configuration.
So now that we've decided to choose our array, we need to test it. And in order to test this, we're going to use the wind tunnel facility downstairs in the fluids lab. The one that we've chosen, we're going to 3D print our turbines in order to use them on small scale. And additionally, to get some visual aspects, we're going to use a high-speed camera. And in conjunction with that, we're going to use the 2017 stable light laser and a fog machine. So as the fog travels downstream of the wind turbine, we'll light it up with the laser, and from above, using high-speed camera, we'll be able to see the vortices that are created. In addition to this, the equipment that we'll use is a vane anemometer. We're going to use this to get the wind speed upstream of our turbine array. We're going to use some velocimeters within our grid that we're going to choose so we can get air velocity readings downstream of our turbines. And we're going to use various pressure sensors as well. So to start off, we're going to start off with the safety orientation, because safety is number one during the entire process. As you can see in the top right-hand side, we're going to do the bottom of the wind tunnel in a grid pattern, and we're going to keep our turbine at grid point A3, and this will not change throughout our entire exercise. Once we set up all of our equipment, the area will be cleared, the wind tunnel will be turned on, the fog machine will be turned on, the laser will be turned on, and we'll run our tests. So for example, our velocity readings will be at B, C, D, and E at specific points. We'll run our wind speeds from 2.5 meters per second up to 12.5 meters per second in 5 evenly spaced intervals. Run those tests, go back, change the location of velocity meters, and then rerun the tests until we get velocity readings for each point within the grid. So as you can see here, for our single turbine configuration, the velocity meters will be in certain grid point locations, and from this we'll be able to determine whichever one has a higher velocity readings. That's where we'll choose to put a second turbine and do our second turbine configuration. The point of this is to get a higher power coefficient within the downstream turbine. We'll get a base point from our initial one at A3, and then if our power coefficient is equal or above the turbine, the one in the back, then that's a positive reading for us. And from this, we can go further into a 4-turbine array, and hopefully we'll get into a configuration that all turbines have an equal or higher power coefficient, the initial one in A3. And from that, we'll use this to go full scale.
So prior to the start of the project, we developed a project management plan to ensure the project went efficiently. So one of the things included in this included the project scope, the parties involved, the roles of the team, the available budget, materials and resources, a risk management plan, and then some project management tools. Our path forward for the project, we're going to implement the experimental plan as discussed. We're going to determine a highly efficient array configuration and verify with CAD simulations. We're going to scale up the chosen array to implement in a rural community, and we're going to deliver a full-scale cost breakdown, power production, and environmental assessment to the client. That's our presentation. Thanks for listening.
Thank you.
Cool.
That's it. Let's see the time.
So yeah, it's about
You imagine it was like
14 minutes,
9 minutes?
13 minutes.